Rightio, so we've talked about stress, which is a measure of the size of the force and the area of the thing being squashed or stretched. And then we've talked about strain, which is a measure of how much it changes, how much it stretches or compresses compared to its original length. And what we want to do now is bring those two things together and be able to get a measure of a type of material. So something with a small stress, I'm not putting very much stress on it, but it has a big strain, so it changes a lot. So just give it a gentle push and it squashes quite a lot. It's quite different from something that I have to really push and it doesn't change very much. So these two things together give you a measure of the type of material you're working with. And what we use is a thing called the Modulus of Elasticity, which is also often referred to as Young's modulus. Yep. And the symbol we use for that is a big capital E. So it's Modulus of Elasticity or Young's modulus. And the formula for that is that it's stress divided by strain. Okay, so something which is very easily squashed would have a small stress and a big strain, so that would come out as a low number. So squashy things have a low modulus of elasticity. Whereas something which is very rigid, which doesn't squash easily, takes a big force to get a little change. So that has a very large E. Those two things go in the same direction. Okay? A big one here and a small one here, both force E to get larger. Let's think about the units for a second. So the units, well, stress is in pascals and strain has no units. So no units doesn't affect pascals, so the units for this thing is also going to be pascals. And in fact, typically, it's gigapascals in engineering terms. A lot of things, steel is typically somewhere around about 200 gigapascals is quite a normal sort of number for the things you're going to be working with. And with these three formulas together, we can get a handle on how much things are going to deform by when we apply a compressive or a tensile axial force. Let's have a go at doing an example. So a steel bar, Young's modulus 200 gigapascals, has a diameter of 20 millimeters. If a force of 100 kilonewtons is applied to 576 millimeters of this bar, how much will the length change? Okay, so we've got 576 millimeter long chunk of this 20 millimeter diameter bar. We're going to, doesn't say whether it's compressive or tensile, but let's imagine that we're squashing it. So we're trying to compress it. The answer will be exactly the same if we're trying to stretch it. So we're trying to squash it up, and the question is how much does it change by? How much does that length change by? Okay. Now these things require a little bit of thinking to get them sorted out. They're not too bad, but it's definitely worth looking at the numbers you've got and thinking which is which. So, well, this one's not very difficult. It tells us E is 200 gigapascals. Although giga is 10 to the power of 9, so E is 200 times 10 to the power of 9 pascals. That's E. Has a diameter of 20 millimeters. Okay, so none of these formulas have diameter in them. So effectively, this diameter is going to give us the area. We have to do a little bit of working to get the area out of it, but that diameter is going to tell us the area. So let's just work that out before we get started. So area is pi d squared over 4. There's pi lots of, let's put it all in meters to be on the safe side, 0.02 squared over 4. And we can push the buttons on the calculator, and we come up with, let's put it on first, pi times 0.02 squared divided by 4, 0. Lots of zeros, 314. 0.000314 square meters. Okay? So whenever you're dealing with one of these things, you've got a diameter, or it tells you it's a square shape and tells you the sides of it, or a rectangle, whatever it is, you need to work out the cross-sectional area. Definitely something that's worth doing. Okay, so a force, so this is F, is 100 kilo newtons, is applied to 576 millimeters of bar. So that's our original length. So that's L, and let's put it into meters, 0.576 meters. Always smart to put things into basic SI units, meters, square meters, newtons, pascals. Then all the formulas work with no drama. When you've done a lot of them and you get good at it, you can play around with things like kilonewtons and square millimeters, gives you megapascals, gigapascals actually for that one, but you can play. And the question is, how much will the length change? So the change in length is what we're trying to find. Okay? So there's a couple of ways of thinking about this. You can either go, what am I trying to find, and pick a formula that gives you that, or you can just go, what can I work out, and have a play around with it. Let's have a wee think about what we're trying to get to. So we're trying to get to delta L, which means I need this one here is the only thing I need. So to get that, I need the strain and L. I've got L, but I haven't got the strain. So I can't use that formula until I've worked out the strain. So where's a formula with strain in it to work it out? Okay, this one. This formula would let me work out the strain, but to do that I need E, which I've got, and the stress, which I haven't got. So before I can work out delta L, I need strain. Before I can work out strain, I need stress. So here's my stress formula, force divided by area. Yeah, whoa, I've got both of those. Great. So I can drive this formula to get stress. Once I've got stress, I can join it with E to get strain. Once I've got strain, I can join it with L to get delta L. So I've got to work through all three of these formula to make it work. So let's have a go and do it. So let's start with stress is force divided by area. Force is 100 times 10 to the power of 3. Area is 0.000314. So I push the buttons on the calculator. I'm going to come up with 100 times 10 to the power of 3 divided by the answer I had in there before is a really big number. 318 times 10 to the power of 6. 318 times 10 to the power of 6. Stress is in pascals. Okay, so that's great. I've managed to work out the stress. And then I said I was going to put that stress together with E to work out the strain. So I'm going to use the formula E is stress over strain. I'm trying to find strain, so a bit of rearranging. Strain is stress divided by modulus of elasticity, just the old bit of algebra in there. Put the numbers in. The stress I've worked out, 318 times 10 to the power of 6 pascals. And Young's modulus we were given, 200 times 10 to the power of 9 pascals, which is that number divided by 200 times 10 to the power of 9 equals 0.0016. 0016. Units, none, because it's pascals over pascals. I've got the matching, there's no megas and gigas and things left. I've actually got the matching, so I'll just cancel out no unit, which is what we wanted for strain. So it looks promising. So now I've got the strain, and I've got the length, so I should be able to work out delta L. So strain is delta L over L. Rearranging, delta L is strain times length. Numbers going in, strain I've worked out here, 0.0016 times original length, 0.576 of a meter. push the buttons on the calculator, times 0.576 equals 0.00092 units. That was in meters, because I changed it to meters. I multiplied it by no units, so the answer is still meters. And if I wanted to, I could say that's approximately equal to 0.9 millimeters. Okay, so I can actually work out how much my bar is going to compress by or stretch by when I apply a particular force to a particular length of the bar. A little bit involved in that we have to use all three of these formula, but a very typical sort of question. You'll see ones where they give you everything except for Young's modulus, and ask you to work out typical Young's modulus. You'll see ones where they tell you everything except they ask you questions like, what diameter bar do I need to be able to carry this load? In which case, effectively, you're trying to work out A. So you need to start with this piece and work backwards to find out A, and then work out the diameter. But this is a very typical sort of approach where you have to tie those three formulas together. Okay, so the key here is that Young's modulus is stress over strain, and that gives you the third formula, and together with those three formula, you can do all these sort of things. Okay, have fun with them.